Hello everyone. Today we are going to be starting with applications of differentiation. Remember, we talked about functions which were not defined at a certain point, and we thought about what can be done with these functions. And it was the calculus which gave us an answer that limits could be applied and we could still see something happening around that point where the function wasn't defined. So what we're going to do now here is we're going to look at the behavior of the functions. And in this behavioral study of the functions at the point where it is defined or not defined on a certain interval, we will be seeing how the functions show us there's a maximum value or a minimum value, which basically we call the extrema on an interval. That is today's session, the extrema on an interval. So let's look at the things we have covered so far and further on. So remember, we talked about differential rules, power rules, product rules, quotient chain, and implicit differentiation. We also looked at trigonometric and higher order derivative functions. As I said earlier, we're going to be defining the extrema of a function on an interval. Specifically, we're going to study the behavior of the function on that interval. And at the same time, we will apply the derivatives in helping us finding where the function has a maximum or minimum value. So I'm going to start with the example for the extrema of a function. Now, let's look at this example. Notice what's happening. If you look at the bigger picture, there is a very, deep value. It's like a valley here. And then you see this little small hill here and a very, very small valley happening around somewhere near 0.5. Now, we would like to study why. What is happening around here? Because otherwise you see the functions going down, going up and down. But these are some points to be noticed. Okay? And that's where we're going to start studying is what are those points on this graph of this function where we see has it a possibility of a horizontal tangent line? Let's look further into it. So let's look at those points first. Let's look at this point, say A. Okay. This is like the deepest point of this whole function. Okay. Let's look at a point B here. Very close, okay? This is like a little small hill. And then let's look at a little point E here. Very close. I can't even say it, so it's just going to write it down. Where you see this little bump down? That's the point I'm talking about. Okay, so if I approximate these values at A, B, and C. So let's look at A. A is a point, say, negative 2.25 and around negative 22, say. Let's look at the point B. Let's look at the values for B. B could be, say, negative 0. 7. Okay, so negative 0.7, a very, say, 0.01 value. For C, let's look at the point, could be approximate, remember guys, okay? Say positive 0.8. And then value here is say negative 0.01, say, okay? Now, notice what's happening around this point A, B's, and C. So let's look at A. What's happening around A? So at this point A, okay? And let's pick up a certain interval around this A, okay? So I'm going to use this little black ink color. So somewhere around A. So if I take some points around A, okay, this is the point around A. What I notice is that all the values in that little interval, so this interval I'm talking about, the value of the function at A is the smallest of all that values. So what we notice, say this is I1. in this interval I1, the value of the function at A is less than equal to every value where x is in this interval R. X belongs to or is in the interval R. Similarly, let's pick up another interval. So I'm going to say, let's pick up a color, say purple for B. Okay, so let's pick up an interval and let's call this interval I2. Okay, so in I2, what do you notice? The function value at B, the point B, is greater than for every value x in this interval I2. I forgot I1 here, guys. Okay, now let's look at a very small interval. Let's pick up another color, say we've used blue, green. What other colors you want? So let's say some, a little darker orange here. Okay, so let's call this interval I3. Okay, so this I3, guys, notice the value at C is like the smallest for every value in this interval I3. Okay, so this A is the smallest in the interval. Rather, if you notice, this A is the smallest in the whole function. So this is this is like the smallest of all the values for the whole function. But B is not the largest, because if you notice the bigger picture of this function, the values keep on increasing. So, but in the small little interval I2, B is the biggest value. Similarly, the C in the small interval is the smallest, but as compared to A's and C's, then A is the smallest for the function. So we're going to look at these ideas of where the functions, are going down and up. All these little maximas and minimas we'll be talking about. So let's go ahead and look at the definition. If we have a function defined on an interval I containing C, then the function C is the minimum of f on an interval when f of C is less than f equal to fx for every x in that interval. Similarly, f of C is the maximum of this function if it is the greater than equal to for every value in that interval. So the minimum and the maximums of a function are called the extrema of the function on this interval. Let's look at some of the observations. Remember when I started with this, I said A looks like the deepest or the smallest value. It's like a valley, right? In the smooth curve you had at B, it looks like a little hill. So this looks like a little valley at A, a little hill at B. So that's what are certain observations for the extrema of a function. Okay, and we're going to talk about that also a little bit later too. So the minima and maxima of these functions are also called the absolute minima and the absolute maximums. Remember, we had the absolute minima. You remember? That was the point A. But these extremas can also occur at interior points or at the end points of an interval. For us, remember, it was at the interior points. Remember the points we had? A, B, and C. Now, if these extremas are occurring at the end points, we call them the endpoint extrema. Let's look at the extreme value theorem now. This is a very powerful theorem. What it says is, if a function is continuous on a closed interval, this function will have both a minima and a maximum on this interval. So let's study this extreme value theorem from a graphical point of view. Okay, so let me remove this. This is the graphical study of this expression, of the theorem. So now notice the second graph in the middle. According to the extreme value theorem, the function is continuous, and if the function is continuous on a closed interval, it's going to have a minimum and a maximum. Okay, so let's look at this one. The function is continuous, but Remember these little open circles? It's not a closed interval. So that means EVT, the extreme value theorem, is not valid. Okay, let's look at the last graph here. The function is not continuous because you have an open circle right in the middle over here, even though the function is defined on a closed interval. So, but it's not continuous. So once again, the extreme value theorem is not valid. Whereas the first graph, the function is continuous, it's defined on a closed interval. Here, EVT is valid. Okay. Remember I talked about a few minutes ago the valleys in the hill? So I'm going to talk about the same here. So here's a nice little cubic function. You could see that you have a hill in the small interval, this little pink rectangle. Similarly, you have a little valley in this little rectangle. So what we see is, because it's a cubic function, it is, keep on going. It's going to keep on increasing as x increases and keep on decreases as x decreases. But in the small little interval, it has a relative maxima, and this has a maxima at the point 0 and 0. And also it has a relative minima at a point 2 and -4. So this is like a little valley. This is like a little hill. So now let's look at certain observations from this relative extrema. It says, when the hills or the valleys are smooth and rounded, the graph has a horizontal tangent line at that point. In our graph previously, this was how it was going. Notice how smooth the curves are, smoother hills and valleys. So we have a nice little horizontal tangent line. But if you have a hill or a valley which is peaked, like this, what happens? Though in this small interval, this is the highest value, this little interval. This is the highest, this peak or this sharper point is actually the highest value in that little interval. Similarly, in this little interval, this point is the smallest value. But notice, these are sharp points. Now, if you recall from our limits chapter, we talked about if you have sharper points, that means the functions are not differentiable at those high and low points. Okay, so let's do a formal definition of relative extrema. What it says is, if you have an open interval containing C, on which the function at that value C is a maximum, then we say f of C is the relative maxima or f, or it has a relative maximum at this whole point. In a similar fashion, if there's an open interval which contains C where the function at C is minima, then we say f of C is a relative minimum of the function. Now the plural of relative maxima is, maximum is relative maxima, and for relative minimum is relative minima. Sometimes we call it local maximum and local minimum values too. Okay, now let's talk about absolute value functions and the derivatives. Here, notice we have a sharp point at the 0. So clearly, from what we learned in our chapters on limit, this function is not differentiable at 0. Also, if you remember the definition of finding the derivative, or using the limit process, we would also see that the left-hand derivative is not equal to the right-hand derivative. Left-hand derivative is -1 and right-hand derivative is 1. So we also can see it from the one-sided limits also, So these are things which we have already done. Now we're going to try to integrate it with things which we want to learn in this maximums and the minimums of a function, but with context to the things we have learned earlier, limits, differentials. Okay, let's do some examples now. We have three little graphs, okay? The middle graph is what we just talked about. This function, the value of the derivative does not exist. So that means f prime of 0. So if it's not clear, so it's f prime of 0 does not exist. We just talked about in the previous line. Let's look at this first graph. Notice there's a nice little hill happening at 3. So we can draw a horizontal tangent line. That means the derivative at that function, because it's a horizontal tangent line, is 0. Now let's look at the sine curve. We have nice little hill at x equal pi halves and a nice little valley at x equals 3 pi halves. So that means when you have these horizontal tangent lines, that the derivative at that function pi halves and 3 pi halves is 0. Now, we are going to talk about a very, very important definition called the critical numbers. So what's a critical number? It says if the function is defined at C, where C is in the domain of F. If the differential of the function is 0 at that point, or the function is not differentiable at C, then C is said to be a critical number of F. Very important to remember, if you have a critical number, first of all, the function has to be defined at that point. Then after that, two things can happen. Either you have a nice little horizontal tangent line at that point, that means the derivative of that function at that point is 0, or the derivative does not exist, that means you have a sharper points. So the function to be defined and either of these two, differential to be 0 or a function not differentiable, those are the points where you have critical numbers. Now we're going to do some examples on finding these critical numbers. Now let's find the critical number of the following function x squared minus 10x. Now to find the critical numbers, now remember this is a nice little polynomial, quadratic functions, and if you draw the graph, this is how the graph looks like. Now this is the point 0, this is the point 10. So clearly we see this has a nice little valley somewhere in the middle of 0 and 10, somewhere here. Now to find that point, this point C, where you see a nice little horizontal tangent line, what you do is you take the derivative of this function. So f prime of x, and you put that to be 0. That means 2x minus 10 is 0, or x equal to 5 is a critical number. Well, let's look at this function, the next one, which is a reciprocal function, 1 over x minus 1. Let's look how the graph looks like. Let's look at the graph here, guys. Okay. Now, we know that at 1, it has a horizontal asymptote, and the graph goes like this. So notice, so what we notice, to find the critical numbers, first of all, the function has to be defined. So one function definitely is not defined at x equal to minus 1. So the other things is, do we have smooth little hills and valleys? When you look at the graph, we don't see that, but let's do it analytically too. So let's take the derivative of this function. So when you differentiate this function, what do you get? Minus 1 over x minus 1 squared. Now this is not possible. You cannot have minus 1 to be 0, right? So that means there is no critical numbers. Okay, even from the graph it is very clear. But when you don't have a graph, how do we do it? Is we take the derivative of the function and also make sure that We don't pick up the points where it is not defined, because the first thing about critical numbers is the function has to be defined at that point. Okay, one more example, guys. The function x minus 4 over x squared. Okay. So when we draw this, let's look at the graph of this function first. The graph of this function, notice at x equal to 0, what is it? That's this y-axis actually is a vertical asymptote. And the graph goes like this. In some way like that. And this point is minus 2, by the way. You can see a nice little, there's a nice little, you will see that here. Okay, so clearly the function is not defined at x equal to 0. So that's basically our vertical asymptote. Let's take the derivative. When we take the derivative, what do we get? 1 plus 8 over x cube equal to 0. Or 8x cube is minus 1, x cube is minus 8, or x is minus 2. So here is our critical number. So this function has a critical number called minus 2. And you can see it from here, when you actually see it, if you use nice little softwares, you can actually see it much more better. Okay. As usual, what we do in this class, once we have learned some topics and concepts, we do some practice problems. So guys, go ahead and practice these problems. And next time, we will talk about a relationship between relative extrema, critical numbers, and how do you find the extremas of the function. Thank you.